Coimbatore Geeknight. Our topic today is demystifying LLM hyperparameters, and we have with our speaker Raju. He's a principal consultant here at Thoughtworks. This will be a hands-on session, so I request everyone to bring their laptops, and we will be posting a Google Collab link in the Zoom chat. If possible, I request everyone to open that Collab link and try running it once. Try running all those cells. Did everyone find that collab link?
Okay, we'll paste it in the Zoom chat. Good evening.
Everyone got the link to the collab.
Good evening, everyone. I hope people in the Zoom call is able to hear me well.
Yes.
So there is a link posted in the Zoom chat. I request you to open that and keep that ready. But let me start with my presentation. Okay. I think it's better if I stand here. Okay. Good evening, everyone. Today we are going to discuss about the much discussed LLMs. So you might have heard the term everyone quoting the LLM as a black box, right? We don't know what is happening inside the black box. We just give the prompts, and magically we start to get the answers that we are looking for. So what we are going to do today is going to open that black box, right, and see what is inside. Okay, so that we don't do trial and error kind of development when it comes to prompting generative AI applications. We will open this box, see what is inside, and try to make sense of it, right? And I wanted you to be comfortable working with LLMs in understanding the black box. And there are a lot of hype going around this AI and LLM. Once you understand this black box, right, you will cut out all the noise that is happening in the industry. You will be at peace. You will not worry about your job. That you will be confident that AI is not going to take my job away. Okay, I want to build that confidence today because we are actually going to dissect an LLM open, see the internal contents, just like what we did in our biology lab, cutting open the frog, seeing the internals, right? We are going to do such an exercise today. Okay, so with that intro, let's get started. So we are going to start dissecting the LLMs first. So those who are very new to this LLM area or AI, right? We need to understand the building block of LLMs, the one that powers the LLM. There are at least two major building blocks, or the important building blocks that makes the LLM today what they are today. The first one is called neural networks. Okay, neural networks is not a new concept. It is there for decades. Okay, so the building block is neural networks, and the second thing that what makes LLM what it is today, what we know as generative AI, is transformers architecture. Attention is all you need is the paper which made the transformer architecture popular. So these two things makes this LLM, okay, as a building block. So how a neural network looks like is something like this. Okay, to start with, we are starting with an abstract understanding. Okay, we will dive in, and actually when we dissect the LLM, you will understand it clearly. But for the abstract understanding, be with me, even if it is not clear, that things will start to unfold. So the way neural networks is organized is that, in the terms of layers, okay, you will have an input layer and output layer. The concept of neural network comes from the inspiration from our brain function, how our neurons are wired with each other, how they communicate with each other. Okay, so it is inspired by that terminology, and the layers roughly represent our different systems of the brain. Okay, so you will have input layer and you will have multiple hidden layers. So for the representation, I just gave one layer, but there will be enough number of hidden layers in between. Finally, we will have an output layer. This is the basic construct of a neural network. Now, how many of you heard about the LLMs which are open sourced, like Llama, Gwen, DeepSeek kind of LLMs, right? Can we go and see what they are made of? We just heard the names that they do wonders and all. Now let's get comfortable and start dissecting one of the uh, open source model. So first thing, whenever someone says, okay, we have a new model published. Um, by the way, I did not give my introduction properly. I'm an AI architect in Thoughtworks. So I need to be up to date, what is happening in the industry. So when someone says that, hey, we have a new model, how do I assess that model? Is that, first dissecting the model to understand, what it is made of, right? So this is how I approach it. So if you go to, how many of you know Hugging Face? Almost all of you know, right? Hugging Face is the platform that hosts all the machine learning models and the LLMs and whatnot, data sets, and even AI sample applications and stuff like that. So I'm in Hugging Face. I've taken a Gwen 3 model, which is Gwen 3 0.6b, the very small, tiny model, so that we try to make sense of what it is made of. So this is what we call as model card, right? This model card will tell about what the model is capable of doing, right? How do I write my first hello world snippet with that particular model, right? So this is what you see in the model card. So this is for the general public, whoever is generative AI application developers. They can refer the model card, take the hello world script, try to run and make sense of the model. Now, for those who want to deep dive and dissect the model, so this is the place where I want you to look at. Go to files and versions. You'll see this primitive list. I don't know whether this is readable for all of you. I'll try. Okay, this is better readable, right? So these are all the list of things that a model repository contains. Okay, I want you to focus on three things. Okay, first thing that you will notice this model.safe tensors, right? And that will be the biggest file in the entire repository. So this is the black box itself. Okay, this is what we call as large language model. It's a binary blob. Okay, this is where the weights of the trained model is stored. Okay, the next item that I will look at is something called as config.json. Okay, this config.json will inform me about what this black box is made of. This 1.5 GB sized file which I have as a LLM model, trained model, what does that contain inside? Okay, so I go to config.json. So this is the first place that I visit. There will be, umpteen number of parameters that will be there. Don't bother, don't freak out. The things that you need to, notice are very few. Okay. The first thing that I will notice is that, the vocab size. This is the vocabulary size. Okay. So what is a vocabulary? Vocabulary is something for we human beings that vocabulary is something when I speak English language, right? English language has a vocabulary, right? A fixed set of words, okay, upon which, I construct my sentence, or so I have an abstract idea to be communicated with you. And how do I construct? I, gather the vocabulary of a specific language, maybe Tamil, English. Depending upon the language that I select, I confine my vocabulary to that language and selectively pick the words, arrange them as a sentence, and to make the entire idea, I kind of join the sentences together and finally, convey this idea to you. This is what happens in our brains, right? Same thing happens with models. So the vocabulary size tells me that what is that the number of words or what we call as tokens, right? In LLM terminology, we say as tokens. So tokens is a construct which roughly translates to a word, but it need not be a physical word. It could be, even broken into, 2 or 3 pieces of a word. Okay. So this vocabulary is made of 1,51,936 tokens. Okay, it's a huge number of vocabulary because this model is capable of talking almost 15, 16 different languages, including Mandarin, Hindi, English. Okay, so it includes, all that tokens as a vocabulary, right? Then what you need to notice is the number of hidden layers. Okay, the number of hidden layers is known as 28. So refer to the neural network diagram that I showed in the first slide, right? There will be a hidden layer. There is an input layer and there will be a set of hidden layers, and then finally the output layer. Now the number of hidden layers says me, how many hidden layers are there. So as an AI architect, this will, like a doctor, once you, see the pulse of when the doctor assess the pulse of the patient, they will know, what kind of troubles the patient is going through, right? So this number of layers will tell me, like, what is the articulative capability of this model? Where can I position this? So this combined with, there is one other parameter that is called, max position embeddings. And then there is one called as where is it? Hidden size. So we will see that in the, dissection visualization that we are going to see. But, only, this much of information is good enough for me to, construct the entire, the size of the model and, assess, what, in which segment that it can fall. Is it a small model? Is it big? Of course, you can determine with the size of the file size of the model. But if you drill down deeper, it will also tell you like the entire neural network architecture, the number of layers, the number of embeddings. So ultimately, the max parameters of the model. We say that, GPT 7B. This particular model is made of 7 billion parameters, right? How do we arrive at that those parameters is using these values, the number of values, the hidden size, the intermediate size. So if you multiply, so there is a formula available, and if you use that formula, that will give you the parameter. I mean the total parameter size of the model. Now coming back, is there any other information that would be useful? Okay, let's just keep things simple. So we know vocabulary size, we know number of hidden layers, we know intermediate size, and we know the hidden size. So these are all the things we need to just get attention to. And then the next file that I will open is called tokenizer. if you go to the model card again, there will be something called a tokenizer.json. Unfortunately, I think I need to download this to visualize it because the size of the model is, the size of the file is too large. Okay, so in the earlier config, you have seen that this model has 150,000 odd tokens, right? That is what is defining the vocabulary. This is the vocabulary itself. Okay, if you see every token, every word in that vocabulary is given an ID. Okay, and what that means for the model. So if you get a number 0, that means it's an exclamatory symbol. So down below, you will start to see the words appearing. So these are all the words from different languages. Maybe English might appear somewhere in the middle. So you are already start to see the split of words, right? So this is what we call as tokens. And the string that you see is the token, and the number that you see is called the token ID. Okay, and there is a process called encoding and decoding of tokens. There is a process called tokenization, then there is a process called encoding, and there is a process called decoding. Okay, so right now we will go to that, in a stepwise manner. Right now you understand the vocabulary and what the vocabulary is made of, and we know what the LLM is made of, how many layers does that have. These all things make sense right now. Okay. Coming back. So in the internals, we have seen config, we have seen tokenizer. In the input layer, you see the neural network takes the numbers. It doesn't take the words. Okay, it doesn't understand the words. The entire neural network is a mathematical construct. Okay, and everything inside in neural networks is made of floating point integers. Okay, floating point numbers. So you will not be injecting any string there. Anything that you give it as a prompt or whatever gets converted into a number, and the number is fed into the neural network. So in the input layer, the number of inputs that is there in the input layer is equal to the number of tokens in the vocabulary. Now, what is the input layer number of neurons in the input layer of the Gwen 0.6 model that we have just seen? Any guesses or any answers? Exactly. That's the right answer. It is equivalent to the number of tokens in the vocabulary. Okay. So when you how do we enter it? Is not going in sequence, rather it goes in parallel. First we tokenize, and that particular neuron will be fired. Okay, that's how the brain communicates. The neurons fire the next neuron, and the next neuron fires the next to next. That's how. So let's say I'm saying today's weather. Okay, today is a token, weather is a token, and today will get converted into a number. Let's say that gets converted into a token number 15. Okay, so when I input that today's weather, that today's will get converted into token number 15, and the 15th neuron will fire. That's how the neural network knows that the first token that has arrived is today. Okay, then I input the next token, which is weather. Weather token ID is, let's say 57, then the 57th neuron gets fired. Okay, this is how the input layer mechanism works. So far you are with me? Okay, now what happens in the hidden layer is magic. Okay, we are not going to get into that. There is a separate visualization available for this, which the resource I will share it with you, because if I start going in there and start explaining that, that will take a 6-month course. Okay, it's not even 1 hour talk, so that I will leave that resource with you to deep dive if you are interested. Then finally, everything gets processed in the hidden layer. When it comes to the output layer, today's weather, then the next token, possible token is, right? Today's weather is. Then if the is token translate to 46, then the 46th neuron in the output layer will fire. That's how the LLM gets to know that, what is the next word that I need to display to the end user. What we have input 2 words, today's weather. Okay, it predicted that the next possible token is, and it is, the token ID 46, and the 46th neuron will fire. So this is how the orchestration of the next token prediction happens. Actually, the output layer, right? It's not as simple as I told, like the 46th neuron will fire, right? It is a set of probabilities. We'll also see that in the hands-on exercise. We'll see, how the probabilities work out. For all the output layer neurons from token number 1,51,000, whatever is there, all neurons will fire. But all neurons will fire with their, probability. What is the probability of today weather New Delhi? The New Delhi will have a very low probability, 0.001. But the word is has a higher probability of, say, 60% coming next. Sorry. So that's how, we, drill down to that next probabilistic token and take that value. We'll see that in a hands-on exercise. Okay. Now, how do we make sense of this, right? This whole thing of, this LLM being a black box, right? If you want to understand it in a very simple construct or term, think of it as a mathematical function. We are not, going into any higher order mathematics, just a basic elementary mathematics. Elementary mathematics, you have how do we design problems, right? So this is the line equation. Mx plus c is a equation of a line, right? So which has, three parameters, m, x, and c. Okay. What is this? This is a 3-parameter model. This is a when you convert it into ML terms, this is a 3-parameter language model. If I convert with only 3 parameters, this equation will become a 3-parameter model in ML terms. So when I say 7 billion model, what does that mean? In that particular model, there are 7 billion different parameters like that, which determines what is the next probability. Why do we need such a huge thing? Okay, let's take case by case. Let's just understand this mx plus c. Mx plus c, actually in real world allows us to model several things. Okay, for example, I want to predict the price of a house. Okay, that I want to buy. How do I predict that with mx plus c? What is the x? X is the square feet of area that I'm trying to purchase, right? This building has a, let's say, 1,000 square feet area. Okay. Then what are the variables that is standing between me and decision? Is the, how much is per square feet value, and what is the registration value, right? Registration value is, almost C, constant. And the value of per square feet is what going to differ from place to place. I can apply the same formula. The formula is same for Singanallur and Saranambatti, but the variables will change. There will be a different value for Saranambatti. There will be a different value for Singanallur. You get the point? So the parameters vary. 1,000 square feet building in Saranambatti, once you determine M and C, you'll be able to get the value of the house, right? So that's how a simple prediction works. That's how we apply the mathematical functions to predict a particular useful domain. Now, going to the LLM area, that's also roughly an equation, but that models the entire real world. Okay, so the the math is at a massive scale, But if you look at in the mathematical terms, it is very simple. You are predicting the problem that we are solving is we are predicting next token. That's it. We are not solving the world hunger. The problem is simple. Always any LLM that you take, the token-based conversational LLMs that you take, they solve only one problem, which is next token prediction. What comes next, right? It solves that problem. And how does that solves that problem? What is the function? The function is made of three things: context, hyperparameters, and there is something called theta. Okay. What is context? Context is nothing but what we input to the LLMs, which is nothing but prompt. We are saying, intelligently constructed prompt engineering, blah, 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 blah. You construct saying, hey, this is my homework. This is how the equation looks like. Can you help me to, finish my homework? So this construct is, what forms the context. Then there is something called hyperparameters. That is what the intent of this particular discussion. Okay. Think of these hyperparameters as the knobs in front of the pilot. You adjust a particular knob, there is a function that happens, right? There is a change in output, right? So that is the hyperparameters that we will explore. Then there is something called theta. Theta is something that we don't have any control over. Okay, theta is the blob itself, the black box, what we call as black box. What you have seen as a file in 1.5 GB, right? That content is called theta. Theta is nothing but the trained weight. They have exposed to training and constructed and cooked that theta. Okay, and we don't have any control over that theta because that theta was modified by the big tech companies who trained that model. So far clear? There is no rocket science here. Okay, I'm also not diving into the higher order mathematics here. Simple mathematics. The prediction is going to predict the next token, and it involves only three different things: context, hyperparameters, and theta. Context is in the form of prompts. Hyperparameters we are going to discuss. Theta we don't have any control over. Clear? Now, what do we have control over? Two things: context and hyperparameters. Context prompt engineering, everyone know. By now you should all know how to write a proper prompt. Now we will focus on hyperparameters. And this is what every developer in the industry does with trial and error. So that's why the intent of this session is to make you aware of what these hyperparameters are, and if you tweak them, what changes you will see in the output. At the end of the session, I do have an exercise, and for that exercise, you will tell me the answer. Okay, right. Okay, so this is the for those who want to deep dive the dissection, right? How the higher order mathematics and how the whole blob, the black box looks like. This is the real dissection of the frog. Okay, so this dissection is for a model called a Nano GPT. For GPT-2, the model looks like this. For GPT-3, it looks like this. We will show the if you want to go and see each and every block, it will take a lot of time for GPT-3. So I'm going to just focus on Nano GPT. So if you so this is a complete courseware actually. Okay, you can just press this space. It will go and start explaining each construct. So what you are seeing now is the input layer, and the characters that you see is nothing but the inputs given to the LLM, which is nothing but prompt. Okay, and then how the tokens go in and what happens in each of the steps, how it gets processed by each layer, that is there in this. I'm not going to walk through this. This entire thing, what the dissection that you see here, this is transformers architecture, folks. Okay, all this, the mathematical notation and the technical diagram that you see on the left-hand side, is the visualization on the right hand side. If you want to, if you have time, you can drill down to the entire courseware. One thing that will definitely make you, if you spend the time, that an expertise in this particular area, ML area. This actually needs a good understanding of maths, and especially the area of matrix algebra. Okay, the dot products and the multiplication product of matrix. If you understand that that part of mathematics well, then I advise you to take a look at it. But for the rest of us, let's ignore this. Okay, for the sake of our own sanity, I'm just going to skip this. It is even it was hard on me. I tried to learn this, but this is not for me. Okay, going back to our presentation. Now we go to the interesting part. I want every one of you to open this Colab notebook. Everyone have this open. When you open this Colab notebook, I want to make sure that you get a T4 here. Okay, connect T4 need to be there. If not, then you go to change runtime type. Make sure you select a T4 GPU and say save and click on connect. And I also want you to do one more thing. Once it is connected and you see a green tick mark here, I want you to go runtime and select run all. Because this will take some time. Okay, let's use that time to discuss the presentation. Hit run all and come back to this presentation. Okay, so what are we going to explore in this hands-on session? We said we are going to explore the hyperparameters. There are a lot of hyperparameters available. Okay, and largely it is split between two major categories. One is called the inference hyperparameters, and the other one is called training hyperparameters. Okay, what we are going to see today is inference hyperparameters. This is by and large used by all GenAI developers. Those who are prompt, those who use OpenAI's API or Claude's API, they in and out use this knowingly or unknowingly. The intent of this entire session is to make you aware of what these parameters are and how you can get best out of this. If you know how to control this, you know how to control your generative AI application. That is the crux. Okay. So the first parameter is called temperature. Okay. Let's see what temperature is. Okay. Consider LLM as a man or a human being, not man, woman, any human being, right? With a glass like this, lens like this. Okay. It is wearing a glass. Okay. The glass defines how I see the world, right? If this is a tinted glass, I will see a tinted world, right? It's not that the world is tinted, but my glass is tinted, but my perception will say that it's a tinted world. Is it? You are getting it, right? So temperature actually controls the fogginess of the glass. So this is what to say? This is an example. Okay, don't take this in literal terms. There is nothing called as fogginess for LLM. To make this understand, to make you understand. Let's say the first picture, right? There is a cat sitting outside the window. So there is a scene, right? Right now I am wearing a glass which is not tinted. Okay, it's a crystal clear glass, so I'm able to see through. There is a cat sitting, there is a yard, and there is a compound wall, and there is a building behind that. I can see every detail clearly, right? But when my glass gets tinted or foggy, what happens is that the details go missing. Is that clear in the second picture? And what is the perception that I get? The first picture, it is very clear that whatever is standing there is a cat. But the second picture, I'm not sure. It could be a dog. It could be even a lion. It could be even a cheetah, right? My perception is not clear. Okay. So when I set this temperature, what this does is it controls the randomness, which I call fogginess. Okay. If you set the temperature too high, then it is too random, meaning it is whole cloudy and foggy. The LLM doesn't see the world clearly, the world that it has been trained for, and the input that you are giving, everything goes for a toss. Okay, we will see that in the hands-on. Just try to grab these concepts. So once you see the hands-on samples, you'll get a clear understanding. Once the temperature is high, it will become too random and creative. If it is too low, then I see the world really sharp. I can see every detail, to the shoes that the person is wearing, to the color of the shoe and the logo in the shoe, everything that I can see it very clearly. But when my glass is tinted, then I start to miss the details. You get the point, right? So when you change the temperature, you are actually blocking the view of the LLM in a good way or bad way. Okay, this is the understanding that you need to take. Okay, and each of this has its own application. We are not saying that setting high is wrong, setting low is correct. No, each setting has its own application area. You just need to understand that what is the end effect that this has. This end effect is this, and let's jump to the hands-on exercise, right? The one that you executed. So by now, the last cell will always fail. Don't bother. We'll come to that. Yeah.
We start the hands-on exercise. Is everyone able to access this Collab link? Okay. If anybody isn't able to access the Collab link, right now we'll be sharing. If you can go to that notepad.link/9ehmt and then copy paste this link, you'll be able to access the Collab. Is everyone able to access it now? Thank you.
Good.
If somebody is not able to access it, please pair up with somebody who's having a laptop and we can proceed that way. Thanks.
Stop sharing. Okay, so we are going to use the same model that we have seen in the Hugging Face, right? The Gwen 0.6b model, which we have seen it in the Hugging Face. We are going to use the same model. I'm not going to walk through the code. Okay, that is not the intent of this exercise. The intent of the exercise is to understand the the three hyperparameters. Okay, so the first one, this particular code block, the cell number 2, it actually loads that particular model in the GPU. So it has loaded it successfully. We see that the model has 596 million parameters, and it is loaded in CUDA. CUDA is the GPU. Now, this is our input prompt. The weather today is. Okay. Every model is a next token prediction model. Okay. We are just going through the exercise of, how does the next token is affected by these three hyperparameters. So we have taken a input text which says the whether today is, right? Now we have also seen that LLM doesn't take human input, human language. It converts everything into tokens. Okay, that process is called encoding. Okay, the string need to be encoded into tokens. Okay, now we are going to see how that encoded breakdown looks like. So this is the original text that we have given. The weather today is, when we encode it, it produces the token IDs. Okay, this is how the token IDs match. Token 0 maps to the, token 1 to weather, token 2 to today, token 3 to is, but this is the numerical arrangement, but actual IDs are the 7859104. You can actually open that tokenizer.json, which we have opened earlier. Go to this number 9104 and see what is there. Okay, this is just an exercise for yourself. So the token, gets converted into IDs, token IDs. Then there is something called, the next token prediction that happens. Okay, the predicted next token, it says token ID 220. 220 is nothing but space. Okay, I have given input to today's weather is, and it has predicted logically is doesn't follow as is with following words, so there need to be a space, so it has given space as the next token. Okay, so this is where I want you to focus, right? When it does that next token prediction, right, how does it arrive at space should be the next token, right? It is not a binary prediction, right? That space confirmed is the next token. The LLM doesn't say like that. LLM says like this: hey, there is a possibility that the next token, the space coming as next token is 13%. There is a 13% possibility for the given statement. Space coming next is 13%, and followed by the token followed by very is, there is a possibility of 10%. So this is how the token predictions are done, and this prediction, this probability prediction, is done for all that 151,000 tokens. Okay, in the output layer, it has got 151,000 tokens, neurons, and each neuron will have output that probability. So in that, we apply a function called softmax, which is taking the maximum probability tokens. And here, the topmost is space. So we logically conclude that space is the next one that need to come. So we do that. Now, the first one that we have selected, temperature. So this is done with a default temperature of 1.0. Okay, 1.0 is the temperature, which shows me the world, without glasses, like, right? There is no glass. Let's also see the probability chart of each token, what this means. Now let's control the randomness. Okay, we will try different temperature settings, like the lowest temperature 0.1 to 0.5. And then the default temperature, then increasing the temperature to high 1.5 to 2.0, and see what happens to the probability. Okay, so with 0.1, you will see that the model confidently saying there is a 91% chance that space is the next token, because 0.1 is the crystal clear detail, of all the world training that I have, the entire world of text that I have seen in my training. The probability of space appearing next is 91%. Okay, when the temperature is 0.7, then the probability slowly reduces. Hey, there is a 20, because I start to get the tinted glass, right? So, okay, I just have a very, rough view of the world. So in that rough view also, I see space as a 25% probability to come as next token. So on and so forth. And when you come at 2.0, right, the confidence of the LLM is gone. It almost sees as, the next 5 tokens as a equal, almost equal probability, like 0.91 to 0.8, there is not much difference. If you see here, these are all huge differences, 91 to 7, 25 to 18. Now all that, probability is gone. Why? Because now I am wearing a very thick tinted glass. I don't get to see my world at all. With whatever little, visibility that I have, with that visibility, I can, associate this probability. So when you tweak this temperature, this is what is happening to the LLM. Is this clear? We'll also combine with the other hyperparameters. The permutation combination we will see, but the impact of the temperature is on the probability distribution, okay, of the tokens. Evidently, if you see the graph, it will be very clear. If the temperature is 1.0, we will get a crystal clear confidence. When we start increasing it, the probability, reduces, right? That is the, so 0.1, it is very confident. 1.0, it is balanced. At 2.0, it is almost uncertain. Okay, right. Now, let's see, I think this is with different temperature setting, but with our input prompt. Okay. What I'm doing here is that with the different temperature settings, I run the same prompt 5 times. Okay, and see, how the output looks like. Okay, with the temperature 0.1, almost identical inputs, which is very deterministic. It is confidently saying, because it is saying 94% space, right? So all 5 times it says, space. When I set the temperature to 1.0, the 5 executions, only 2 executions had space and 3 were different. Okay, the consistency goes for a toss. There is some variation, but it is still reasonable. With temperature 2.0, see, with the temperature 1.0, it is still logical, right? The flow of statement is still logical. With the 2.0, you will see complete craziness. Today, the weather today is out. Do we have such statements in our regular conversations? No. It went for a total toss, right? Now you understand the impact of temperature on the outcome, right? Okay. Now, this should give you the clarity on, when to use what temperature. For factual tasks, code generation and math, you will use low temperature because you want factual output, very confident output, right? For general conversation, right? I will use, anywhere between, 0.7 to 1.0. Don't have any limits, okay? Don't be tinted, okay? Have a clear-cut view. At the same time, don't be deterministic. Don't be, give the same answers again and again, because when a conversation gets interesting, when we start to, articulate better, when we start to, converse in variety, right? So to bring that variety, we'll vary it. 1.5 to 2.0, we will completely use it for what? Creative writing. If you want to write a good storyline, what to say, fantasy story or something like that, then you can go set the temperature too high. That's where the fantasy happens, right? So that's the general idea. Now comes the interesting. So while the temperature actually controls the probability distribution for the output tokens, top P is a filter. Okay. Now that this 1,51,000 output tokens that we have, this top P is a filter at the end of the output layer. You know, assume like that. Top P is a filter. And how does that work? It tries to, you know, accumulate probabilities together until that range is achieved. So you'll see that with an example better. When I see top P as 0.1, then the only token that it gives me is space with a probability of 13, because 0.1 means 10%. So I have already exceeded my quota. So the only filtered token that I get is space. Okay, this is actually reducing the noise. Okay, filtering it out. When I set the top P to 0.5, then the cumulative probability of the, you know, selected tokens available for my consequent executions improves by 9 tokens. So the end effect you will see in the consequent executions, not in the same execution. Same execution, it will still select, you know, space. But this is the, you know, pool of words that are available to the LLM to, you know, actually select one of them, right? So if you run 5 times, you will get to see one of this. Okay, that is the thing. With top P 0.9, the token pool is even more larger, 157. With top P 1.0, this is the you know, maximum value that we can assign to top P. Why? 1.0 means 100% all unfiltered, right? There is no, you know, 1.1 or 1.2 and all, because, you know, 1 is the max. Where you will see that, you know, this 1,51,000 more tokens will start to come. Okay, so this graph shows you, you know, how that top P filter works. Okay, so the same example, what we tried with the temperature, we are going to, you know, try with top P as well. Okay, we don't see any change with 0.1, because it actually filters only one token, right? So all consequent executions, it only shows space. Now with 0.5, this is where I said, you know, that you will start to see differences, right? 5 different executions, you got 5 different outputs, because the number of tokens pool available to that LLM has become larger because of the filter funnel. I have just expanded the filter funnel. More number of words are available to LLM, so it is able to come up with more variations. Even more expanding, you know, you will start to see even more articulative outputs. Okay, temperature controls the probability, top P filters it. Clear? Okay. Now there is one more filter called top K. Okay, this is not as confusing as top P, which is, you know, accumulation of percentages. Top K says, hey, give me top 5, yeah. Give me top 2. Give me top 1, right? Number, fixed number, right? So K is equal to 1, we call it greedy decoding. So I'll tell you what is the effect of K is equal to 1. Can anyone predict that if I set a filter of 1, okay, at the end of the output layer, top K is equal to 1, which means that there will be only one token coming out, always. Even after, you know, multiple executions also, only one token will come out. What would be the end effect? For any use case, any prompt that you give. Monotonous, very good. Monotonous response and kind of a mugged up response. What it has seen in the training data, right? More frequently, it will start to, you know, vomit that out. That is the effect of K is equal to 1, right? And when you increase the K, then the articulative capability of the model improves. Okay, it gets a, you know, better articulation. Okay, now cutting to the examples. So when we set top k is equal to 1, it has taken only one token, top k equal to 5, it has given 5 tokens. So the end effect of top p and top k is filtering. And this is how the affect the number of tokens available to LLM for articulation in the consequent executions. So this is again a graph explaining that. Where do we apply this top k? So we'll also go through the same example. The end effect you might see it is same as top p because both are filters, right? Which controls the articulative capability of the LLM. But the kind of cases what we use is like this. Temperature, you use it to control the probability distribution, the general clarity of the LLM. Do you want the LLM to be creative or do you want the LLM to be factual? If you want to be factual, set it low. If you want to be creative, set it high. If you want to be in between, select a middle value. Now with nucleus sampling, how do you cut out the noise using top P? How do you cut up the tail? If you want to just cut out the tail, use top P. If you want to be really, really deterministic, if you want a very deterministic output, every time when I execute the prompt, I need to get the same results. If that is the kind of application that you have, then you need to choose top K. Okay. So I think there is now these are all the real world generation examples, with the different combination of temperature and top P. So these are all kind of industry recommended practice for a chatbot. We will use temperature anywhere between 0.6 to 0.75, top P to anywhere between 0.9 to 0.95. Code generation is factual. It's a very logical thing to do, right? Anything that involves logic, you don't want the model to be creative. You want the model to be factual, right? So we will use a lesser temperature like 0.2, and the filter can be the combination of any two. I mean either top P or top K. I would recommend from my experiences choose top K, and depending upon which coding language that you are working, tweak that. Okay, if I'm working on SQL statements where the SQL's vocabulary is very limited, right? SQL vocabulary is very limited, I'll set case equal to 10. But if I take Python's vocabulary is pretty large. So I might even go and set case equal to 50, right? That language determines that. For creative writing, you can set the temperature as high as possible. If you want a fantasy story, you can go as large as 1.5, right? If you are going, in between, like, translation and summarization, you can, choose any of these values, right? And you will see the outcome here. What I want you folks to try is go and, change the temperatures and the parameters and see the end result for yourself. Let's try that one here, right? Let's take this example of code generation, right? It's whatever the model that we have taken is a very small model. Please, take that in mind. So the code that it generates may not be up to your expectation or standard. Don't blame me. Okay. So this one takes top K to 10. Okay. Now with the top K to 10, let me just make a note of this, right? There is an expected output 120, expected output 1 is coming. I'm going to execute again. What I will see is I will see a variation from the previous output, either in the form of comment or in the form of a logic flow or in the form of an expected output. You see a different articulation here, right? Right? Between executions, the code actually changes. Okay. But I don't want the code to change. Every time it should deterministically give the same code for me again and again. What should I set? K is equal to 1. Okay. So I run it first time. It will give some result. So it has given this result. I execute it one more. It will be ditto same result again. Okay, this is how we bring consistency into our generative AI applications. If your application expects same factual result every time in the execution, what hyperparameter you touch, top K. Okay, right. Now let me go crazy and bring top K to 100. What will happen? The LLM will become chatty. You'll see that. In between the course, see, it has started writing notes and all. It becomes so chatty because the number of tokens that are available to it is too much, right? It has the luxury of spending, right? You have 10 lakhs in your account, you will spend it with your wish, right? So that's what is happening. When it is restricted, you get the same and same output, but when you expand it, it just explodes. All right. Okay. Now translation is fine. Okay, the final one I want you to answer. So I have an application for answering MCQ questions. I have a set of MCQ questions to answer. Okay, it looks like this standard MCQ questions where there will be a question, number of options given in the array, and then it has to tell me, what is the correct answer. Just the option alone, the letter alone. Okay. You will tell me what temperature should I use. Should I use top P? Should I use top K? What value should I use? Yes. Or you can try it for yourself in the Colab itself. Let's start with temperature, right? What value we will use for temperature? Fantastic. It need to be as low as possible because we are factual, we are looking for factual answers, right? Top P or top K? Top K. Why? We need only one character, so that eliminates top P. I need how much top K? With that, we execute. Bingo, we get the predicted answer, single character always. So now you know how to control this black box, just 3 parameters. Right? That's all, folks, for today. We can take any questions. No, there are many, but these 3 are the major. So if you know these 3 parameters, you can confidently build 80% of your generative AI applications. So I went for that Pareto. You just take that 20% of the parameters, which will cover the 80% of the use cases. That is this. There are also several other parameters like seed and others, which is not important. If you are actually building a deep tech product, then you need to deep dive onto that. But for the general full stack generative AI developers, this is good enough. There are also full set of hyperparameters on training that we will schedule separate Geeknight. I don't know whether that will fit in the Geeknight time frame because that needs a workshop, because there are so many parameters, they are all connected. You can't isolate one without the other, and the execution takes a lot of time, right? So we may need to plan that out. But so this is the direction. You can just start reading about this. Now with this, now you tell me, is AI going to take my job away? At the end of it, bloody it is only predicting the probability of the next token. How can that simple thing come and challenge me? Right? So we take, see in probability, you understand probability, right? When probability hits 99.9, it means accuracy. It doesn't mean intelligence. You, you understand that. If you have that understanding, there will not be any fear. Guys, we have attained the utmost accuracy possible. Great. But it's not intelligence. You can name it as intelligence, artificial intelligence, call it whatever you want. Call this AGI. I'm okay with it. At the end of it, the engine that runs is a mathematical foundation. If you understand the building blocks of that, you can control this machine. And if you know the knobs, which knobs to adjust, you will be able to control this. We are on top of this. This will never get on top of us. So that's what you are asking for is actual another session, but I'll try to concise answer. So RAG-based systems are actually for factual answers. Okay. You see that function that I have given, right? It takes three parameters: context, hyperparameters, and theta. Okay. The context is the one which actually refines the accuracy and the faithfulness of the machine. So the best context that you can provide, the factual the answer will be. Okay. You give an ambiguous prompt and try to get a factual output, that will never happen. The ambiguous prompt that you give, ambiguous answer you will get. So with RAG, what we try to do is, try to enhance that, factual thing as large as possible. Then, you will have a better output. Then also there are some grounding techniques available. Once the LLM, provides the answer, then we go and check against that ground reality and check the answer variety, and then so there are a lot of quality control methods around that. So there is something called a model drift. Okay, so model drift happens. You might have built that RAG solution. It might have worked really great on day 1, but on day 20 you will start to see it is deviating. The quality is deteriorating because the data refresh, right? We did not refresh the data correctly because we are working on the evolving data. Let's say you have ragged your business enterprise knowledge base, and that knowledge base every day is being updated by people. If you don't reflect that in the RAG database, of course it will start to drift, right? So these are all the quality control mechanism to measure the drift and measure the there are parameters like accuracy, faithfulness, right? There are data science metrics that are available. So there is a separate framework called ragas. Okay, you go and read about that. Ragas is the quality control framework that is used for this measuring hallucination, faithfulness, accuracy, everything, and it will give you the overall quality of your product. And there are control mechanisms how we can improve each one of them. Yeah, you had a question.
My first two questions that don't need immediate answering is why didn't anyone teach me in such a simple format earlier? And the second question is when are we having the next workshop? You can think about that, and you can choose to answer if you have something in mind. But the next question, which is more relevant, is so let us say that I'm using ChatGPT, and I've already given in a question. So will the KP and the temperature change based on my prompt also? Is there some interplay happening there, or is it static
It's a static one. It's a static one, and that is actually selected by the tech lead or the architect for that particular use case. Okay, so there are different set of these parameters in play in different areas. This is not a simple answer per se. There is no single answer, right? What you see is only a single chatbot. Okay, behind the scenes, there are several agents running and orchestrating. Okay, for each one of them, the temperature, top P, top K, the things will be different. So they kind of, answering your question directly, for the kind of questions that you ask, for them, there is chances of temperature and top P, top K differing by where it ends up. Okay, which agent it ends up. Okay, if it ends up in a summarization agent, the top P, top K will be different. If it ends up with a coding agent, the top K temperature will be different, right? It is not single prompt to answer thing that is happening now. It has era of agents. You submit one request, the first thing that will happen is the orchestrator will try to classify what kind of intent that you want to. Do you want to generate an image? Do you want to code, or are you asking for a factual question and answer? So that classification will happen, and after that classification, it will assign to that subordinate, which is another agent. Okay, looks like this guy has asked for a factual agent. Let me go and pull one of the factual agent who looks at all this and submit it to that. That agent will have one fixed temperature, top P, top Q, and that will answer. I guess you get the idea, right?
Yeah, so I'm just imagining that if I'm asking something very controversial to the same LLM, so then it classifies that as being.
No, that is called guardrail. Okay, so that is guardrailing. Anything that adversarial prompt or antisocial thing that you are asking, that is the first thing that will happen. Even before classification, guardrailing will happen, and it will reject that upfront before even that gets processed by anybody else, right? In any generative AI application, guardrailing is the first exercise that we do. Otherwise, it will damage the brand altogether, because people will start to say, hey, Thoughtworks has built this bot, and it is started suggesting how to bring down the Prime Minister of India. Right, all that will happen. It will happen, huge damage to the product and the brand.
Yes, so I was curious, since you insisted that AI won't take our jobs, what's your point on AI gaining sentience? Do you see that as a possibility?
Sorry,
What is your thoughts on AI gaining sentience, as in its ability to think for itself? Because we are seeing cases breaking out here and there.
Do you think from what you have learned that it will think on itself?
From what you have learned, it is a probabilistic prediction.
Yes, unless there is a change in architectural thing. Okay, there is an active research. I'm not denying that there is an active research going on to bring that capability. Let's think as humans, right? How does the human deal with all these questions and problems? You are asked to write a code, right, at work. How do you deal with that? We deal with that with two things. Just two things. Survival instinct, because I need to get salary at the end of the month. In caveman era, I need to live. Somehow I need to live. But in this corporate world, I need to get the salary at the end of. So survival instinct is the first driver of accepting any problem to solve. The second most and important thing, which is very unique to human beings, is curiosity. That is what is bringing innovations. These guys don't have curiosity. Do you think this has a curiosity? So there is an active research going on, how we can bring this curiosity element into this LLM architecture. That's an active research area. We might get it. Okay, if they succeed in doing that, probably, we maybe, start thinking like, okay, we are doomed now. It's very scary. We are doomed now. Yeah. I will worry only when that appears as a ground reality. Right now, it's not a ground reality, and I'm not worried. Because things like this transformer architecture, it happens once in a while. Happens really, this breakthroughs with my 25 years of in the industry. This is the third big leap that I see that is happening. AGI might happen, I'm not denying that, but whether would I live to see AGI is a question. Will it happen within my lifetime is a question. I will live peacefully.
Raju, another great session from you. It is always delightful to attend your sessions. My understanding or philosophical question, like you're talking about AGI and stuff, maybe LLMs will not take our jobs, and especially your job. Maybe it will take some of our jobs sitting here. The reason is I'm saying the curiosity and creativity. I'm sure it cannot take our jobs.
See, when the industrial revolution happened, this is the same fear. See, we are in an industrial revolution. When machineries, automated machineries came into play, the daily wages were really on the streets fighting. That this machines are taking my job away. This is no different from the blue collar crisis that happened in the last century. It's just that it has happened to the white collars, but we will still survive.
Definitely survive. So the thing is, some of the jobs, maybe it will be transferred or it will be completely changed.
Yeah, so that's the, it's on you. So I'll try to answer the question that he has asked. Like, how come you are able to, simplify this? Because I spent one whole year in understanding this. I did not take even one holiday. I invested, I should not say this amount because then I will get a divorce notice. Because I got a system to experiment with this, and that is very costly. And that I did with my own finances. Spent the whole time trying to be on top of this, because the moment I saw ChatGPT generating code, I lost sleep for three continuous weeks. I know this is coming to hit my bread and butter. Okay, so how do we get better? Try to understand the one which is understanding the enemy is the first trait, right? First understand the enemy. Let's strategize later. Don't bring the strategies first. Don't fight the enemy straight away, right? Understand the enemy, what the enemy is made of, what the enemy's strengths and weaknesses are. That's how I started. Okay. And all this, whatever I'm delivering, it is not available in any book. It's not available in internet. This is all, hardcore experience by doing stuff, seeing stuff. So once that, once I understood the enemy's weakness and strength, now I'm on top of it, right? And, that clarity comes into mind that even if AGI happens, I'll take the same effort and be on top of AGI. I recommend that, every one of you should go through. So when I started, things were real crazy, things were not available. So right now, GPUs are available for cheap. I started 2 years back. That times, GPUs were so expensive. I used my credit card. I used my personal gaming laptop, got a best gaming laptop possible to train models, to understand these hyperparameters that I'm, discussing with you, right? I took all that pain to, drill down, say it's as you get old, right? Your brain stops working. And I'm 45 years old. I don't have that smartness that I had at 20. I might have, done it, you could probably do it within 2 or 3 months. What it took an year for me, you might just do it, within 2 or 3 months. What, is, setting us apart is the drive, the drive towards that. Until, I became, I wouldn't say still I'm on top of it, but at least, people consider me as a expert in this area, right? Until I reached there, I didn't sleep. Until that comfortness came, then, now have a peaceful sleep at night, because, the strategy is there. If the enemy comes to attack me, what is the strategy that we can employ, that is there. There is one resource that I would recommend every one of you to. You can, if you use that resource effectively, you will come and stand here within 2 or 3 months in time. That is called deeplearning.ai, which is done by the industry expert Andrew Ng. It's a very good, damn good resource, and it is available for free. So anything that is available for free is not given serious attention by folks. So the deeplearning.org you visit, there are a lot of short courses on these things. How to build agents, how to build use LLM, how to build the generative AI applications. There are a lot of short courses. You take one short course per week, or 2 per week, whatever your schedule allows, right? At least by end of one quarter, you'll see yourself in a different place. Okay, I wish all the very best. Get your hands dirty with whatever you have learned. Sorry, I did not ask. Is there any question from the online attendees? You can post the question in the chat and I will try to answer. All right, then that's it, folks. Thank you.
Thank you, Raju, for this wonderful. So this took a, how should I put it? It took a lot of worries away, I hope, for everyone. And yeah, so thank you, Raju, a lot for the session. And yeah, and thank you to the Geek Night organizers for organizing such a wonderful session. And most of all, thank you to all these wonderful people who came here. Curious minds such as yourself are what keeps our drive forward in this world of innovation. And I hope we all keep this drive in the future that we envision. So thank you, everyone.
So there are few questions from the Zoom chat. I'll just start addressing. Any resource from QA perspective about LLM? So Ratika, I would recommend the same site to you. This is called Deep Learning. .org. It's already in the chat. Yeah. So there are QA frameworks also available for generative AI applications. You can take a look at them. If AGI is far behind becoming reality, what are all the top AI companies competing against in such space? Doesn't it mean this is a bubble? Jay, I don't want to go into that speculative space. It's a wait and watch game. So what the top AI are doing, I think that should not concern us. Let's focus on what our daily bread and butter job. Can you please repeat on the difference between top P and top K once again? So on a nutshell, top P and top K are the end output filters. Top P filters based on the cumulative probability, and top K on the fixed number. I would recommend that you go through that Colab notebook once again. That has all the descriptions and examples for you to get clarified. Yeah, that's it. Thank you.
Yeah, so thank you, folks. I will not hold you folks much longer. We have refreshments in the cafeteria that you can enjoy. And Have a great evening. Also, before you go, we would like if you share your feedback with us. So we'll share a link to a form. And yeah, please give us your honest feedback, anything we could improve, and like any feedback you could give to the team as well. So yeah, thank you.